Alright, this is a bonus lecture. So we saw with the stars and bars arguments that n minus 1 choose k minus 1 is the number of k tuples of positive integers that sum to n. So remember, this is the number of ways to distribute n identical objects to k children so that each child gets at least one object. And actually, whenever you see a beautiful formula like this, you have to ask yourself if there is a direct bijective proof. Is there some sort of bijection between these two sets, where this is the set of subsets of n minus 1 of size k minus 1? And so here's an attempt to do such a proof. Given one of these subsets of size k minus 1, you can order the elements in increasing order, alpha 1 through alpha k minus 1, and you can define the difference sequence as the difference of any two elements in this ordered sequence, with the caveat that we define delta k to be n minus alpha k. And because of this strict inequalities, you're guaranteed that this resulting difference sequence is a sequence of positive integers. Because alpha I plus 1 has to be greater than alpha I, this number is at least 1, so these are positive integers. Moreover, you can check that if you sum these, oops, there's a typo there. If you sum up these delta k numbers, what do you get? Well, delta 1 is alpha 1, delta 2 is alpha 2 minus alpha 1, and so on. And you start to see that there's cancellation. Alpha 1 is subtracted off, alpha 2 is subtracted off, and so on, all the way to alpha n. In Calc 2, you might have seen this as called the telescoping series. And so all the terms cancel out, and you are left with n at the end. And so the summation of this delta sequence is n. So this actually is a solution to your original equation. So let us define a map from the set of k minus 1 subsets to the set of solutions to my linear equation. And the map is given by setting the subset from the previous slide to its delta sequence. And so this is a function, and you can prove it's a bijection, and one way to do that is to give the inverse function. So letting this set be x, the inverse function needs to take one of these solutions and gives me a k minus 1 subset. So given one of these solutions, a1 through ak, we could define the partial sum sequence. Si is the sum of the first I entries of your k tuple. And since each of these alpha i's has to be at least 1, these partial sums have to be increasing. And so you can group them together, and they form a k minus 1 set. They're k minus 1 distinct numbers. You can group them together and get a set of size k minus 1. We're forgetting the order, but we remember the order we're interested in is strictly increasing. And so to show that these two functions are actually inverses of each other, we do the composition. Given one of these k minus 1 subsets, f is supposed to turn into the delta sequence, and g is supposed to turn into this collection of partial sums. Well, the ith partial sum is the sum of the first I delta sequence entries, but delta 1 is alpha 1, delta 2 is alpha 2 minus alpha 1, and so on, all the way up to the last one, and we see yet again the telescoping series phenomenon, and we end up with just alpha I. And so in particular, G composed with F takes this set back to itself, because these SI's are just alpha i's. So it's the same set, so the T and S are the same. And the inverse bijection works the same. The composition, the other direction works the same way. Given the delta sequence, given a sequence, you create these partial sums, and then you do these difference operations, the delta sequences. But if you take the difference of two partial sums, you actually just get the next term in the sequence. So you actually recover the same thing you started with. And so this actually is a bijection. It should be familiar from Calc 2, except they don't use subsets, they just call them telescoping series. And so that gives a much more natural proof for why binomial coefficients count these solutions and subsets. Because for every subset there's a specific solution, and for every solution there's a specific subset. Now, it's worth pointing out for research purposes in mathematics, this idea about counting solutions to a linear equation can go further. Given an n by n matrix, A, and an n vector B, you can ask about all solutions to the equation AX equals B. Now, if you're working over a field and you're dealing with a vector space of finite dimension, there's going to be infinitely many solutions. And you study this in linear algebra, usually your goal is to find a basis. But instead, suppose that you want to count the number of solutions that have non-negative integer coefficients. It's worth pointing out this answer could be infinity in general, but there are cases where the answer ends up being finite. And so you're studying these equations. The n here is a parameter. You're scaling the vector. And so the number of solutions varies as n varies, so you have a sequence. And this is a common problem in combinatorics. It's called the Ehrhart function. And these pop up in applications in studying lattice points and what are called polytopes, these convex geometric objects. It turns out you can show that a point lies in this object if and only if it's a solution to a linear equation. In fact, actually, usually one works with inequalities. And so there's some sort of matrix inequality that you are a solution to that equation if and only if you're inside this octahedron. And so this is the study of counting lattice points in polytopes is a famous ongoing research area. And I thought I'd mention it because it's loosely related to what we've been doing. We've only been doing the case of one equation and equality, but you can generalize, and there's a lot of research in that area.